Hey, all you Raider haters. Today we're going to talk about implicit differentiation. And what's implicit differentiation? Well, sometimes we have functions or relations, it's probably a better way to say it, such as x squared plus y squared equals 25. And maybe we want something like this, all right? Which would be okay to solve. I'm going to show you both ways here. It'd be okay to solve for y, but we may not want to, all right? And so we can still calculate a derivative without solving. So I'm going to show you both explicitly and implicitly how to do this. So explicitly, if we solve this for y, we get, and so now we have two functions that y is equal to. So this is not actually a function, this is a relation. And that's what happens a lot of times with implicit differentiation is it's not a function, it's a relation, but we can still take the derivative. And so when we take this derivative, it's kind of nasty, but we get dy dx equals, and it's going to still be plus or minus, but 1/2. If you don't remember how to take this derivative, please pause the video, make this make sense to yourself. Okay, then times 2x. Now, in our practice, we would typically just leave it like that and not do anything more with this. So that's an easy example. All right. So let's talk about implicit differentiation. So when we do this implicitly, this is the way we're going to do it here, implicitly, I want you to think, you don't actually have to do this, but I want you to think of this as, and so now when if we were to take this derivative, all right, we'll take this derivative, well, we know the derivative of x squared is 2x, and the derivative of f of x is 2f of x times f prime of x. I don't think I said this. Let me go back here a little bit. Okay, y, remember, is f of x. We solved here, we solved y as a function of x. So that's why we can do that. Okay, that equals 0. Now our goal is to solve for this right here. So when we solve for this, we get, and if this doesn't make sense to you, please pause the video, work that out for yourself. It's just a linear equation. Move the 2x over, divide by 2, we get this. All right, now this doesn't look anything like this, but what I want to show you is that when we simplify here, this 2 and that 2 go away, and so what we get is we have the x over the square root of 25 minus x squared. Well, remember, this is f of x, right? Oh, and I forgot plus or minus here, plus or minus. Okay. So, oh, you know what? I messed something up here. This is a negative here, a negative here. So this would be a negative x, but still that plus or minus takes care of that. So that's where this negative comes from, is this negative I failed to put in here. And so now if we solve this, f of x is plus or minus x over the square root of 25 minus x squared. We put this in for f of x. All right, I want to show you two examples here. One with how we're actually going to do this, and then one with the product rule. So to actually do this, we're just going to do this like normal. 2x plus, now what's the derivative of y squared? Well, that's 2y. But remember, y is a function of x, so we have to use the chain rule here and take the derivative that's inside. That's exactly what we had before. Instead of writing f of x, or f prime of x, we're just going to use y prime. and that equals 0. And now our goal is to solve for y prime. That's our dy dx. Okay, so keep that in mind. Y prime equals dy dx. All right, and so then when we solve this, we get y prime equals negative x over y. And guys, that's how we're going to leave it. We're not going to figure out what y is. We're just going to leave it like that. So you may leave x and y together. All right, and that's what it means to be implicit. X and y are together. There's not an explicit form of what y is. All right, let's look at one more example, and I'll leave you be. All right, so here we have a different one. Okay, and what I want you to notice here is that this is a function x squared, and this is another function. Remember, this is f of x. So how would we deal with x squared times f of x? Well, we'd have to use the product rule. All right, I'm just going to type it. It's a lot faster. We have to use the product rule here for that. So if you remember the product rule, all right, let's take the derivative now. The product rule says I take the derivative of the first. Well, that part's 2x times y plus x squared. Now, what's the derivative of y? It's just y prime. Okay, and minus the derivative of y cubed is 3y squared times y prime. The derivative of x is 1. So notice every time we had a derivative of something that was x, it was just normal, like this one here. But every other time when we had a derivative of y, we have y prime and y prime. Okay, and what's the derivative of 3? Then it's 0. So this is what we have. Now these two right here have y primes in them. Everything else we're going to move to that side. So what do we have now? We have x squared y prime, and through the magic of television we have. And so then notice that both of these have a y prime in them, and so because they both have a y prime in them, we can factor that y prime out. So we have y prime equals x squared minus 3, which still equals 1 minus 2xy. And so hopefully you see now we need to divide by x squared minus 3. And when we divide both sides by x squared minus 3, we get, and so here is our derivative. Notice we have x's and y's together. It's implicit. All right. Now we can do all kinds of good things with this. We can calculate equations of tangent lines. We can find where this graph has a maximum or a minimum. I just didn't show that to you here, but we know that from previous work. All right. Hey guys, I appreciate you watching. I know this implicit differentiation can be kind of weird, so we'll take a look at it in class. We're going to use it for the next couple sections because we're going to do it with respect to time as well, and so we're going to use implicit differentiation. Again, we're going to call it something else at that time. All right. Hey, we'll see you in class. Have a great day.